We introduce here the RIP routing protocol as a common example of distance vector routing. Distance vector routing protocols are a form of dynamic routing protocol that work on the principle of the Bellman-Ford algorithm to define the route that packets should take to reach other network destinations. The application of the Routing Information Protocol, or RIP, is often applied in many small networks, and therefore remains a valid and popular protocol even though the protocol itself has been in existence much longer than other dynamic routing protocols in use today. The characteristics of such distance vector protocols are represented in this section through the Routing Information Protocol. So upon completion of this section, it is generally expected that trainees will be able to describe the behavior of the Routing Information Protocol, as well as successfully configure RIP routing and associated attributes. With the introduction of static routes, we have looked at the manual population of the IP routing table, along with the typical static route methods of application. We now, however, begin to look into the use of dynamic routing protocols and how their application helps to build routing tables and allow for the dynamic recovery of connections in the event that a primary route fails. We begin here by introducing the Routing Information Protocol, or RIP, which is considered a distance vector routing protocol. This basically refers to the protocol's ability to establish routing by specifying a certain path or vector for a destination and the distance based on a fixed metric to reach that destination. RIP relies on a small number of parameters in order to achieve this, which are communicated between routers. As such, bandwidth is required by RIP, as with any dynamic routing protocol, to communicate information between routers, but in the case of RIP is minimized. The RIP routing protocol also has no ability to carry subnet mask information, and this means it cannot specify a different mask based on requirement. Therefore, the subnet mask applied is based on the address. So for example, a network recognized as having a network address beginning 192 will be recognized in binary as being a class C address, and so will be assumed to have a subnet mask of 255.255.255.0. This means that RIP must operate as a classful routing protocol, and as such only use classful IP addressing. Routers operating with RIP will form a routing table containing routes to remote networks in a process of convergence. The convergence process for RIP, however, can be slow and is susceptible to an issue known as counting to infinity, which involves routers being unable to converge. We will introduce the details of this later. However, we should initially understand that as a result of this, RIP was designed with a diameter of 15 routers, limiting traffic from one end of the network domain to the other, whilst also limiting the use of RIP to small to medium-sized networks. We represent the typical application of RIP in the image as part of a single site. In terms of implementation, however, RIP is simple to configure with little in the way of complexity. The primary operation of every IP routing protocol is to allow for the routing table to be populated with routes, to allow routers to be aware of one or multiple paths to remote networks. For RIP, this is no different, and so to allow the IP routing table to be populated with routes, RIP will transmit messages known as route advertisements that carry routing information to the neighboring routers. Route advertisements are transmitted by routers periodically, for which the default transmission period in RIP is every 30 seconds. However, it is also possible to, but not typical for, routers to request routing information from neighboring routers where necessary. In the case of RIP, only the best routes from the perspective of the advertising router will be advertised to the neighboring routers. From the example we see here, RTA is directly connected to network 10.0.0.0. Neighboring routers in the form of RTB and RTC will learn of this network through the advertisements sent by RTA. The receiving routers will also advertise this network based on the best path, such as can be seen between RTC and RTB. RTB will learn the best routes from the perspective of both RTA and RTC. The metric is what is used to determine which route constitutes a better route. In RIP, the metric is determined based on hops, and represents the distance to a given network. A lower hop metric, therefore, is considered a better route. In the case of RTB, it learns of the best and, in this case, the only route from RTA and RTC, and is able to determine based on the lower metric that the route via RTA represents the better route to reach network 10.0.0.0. The hop metric is incremented by 1 each time a packet is to be forwarded by a router. In some instances, it is possible for the routing path and metric learned to be inaccurate, and for those routers operating with RIP to experience routing loops, which we shall look at in more detail in the coming slides. It is important, however, to realize that where this occurs, the router is often unable to converge the route due to the increasing metric value, which, if not limited, will continue to increase indefinitely. This is referred to as counting to infinity, and so RIP puts a cap of 15 on the metric, with a metric of 16 representing an unreachable route. This is so to allow convergence in such occurrences to be achieved sooner, without affecting the general ability of RIP to support routing in small to medium-sized enterprise networks. We show here an example of the means by which a loop formation is possible. In this example, we have two routers in the form of RTA and RTC, and network 10.0.0.0 to which RTA is directly connected. As part of the general operation of RIP, network 10 will initially be advertised to RTC with a metric of 1, allowing RTC to identify the best path to network 10 via RTA. In the event, however, that the connection to network 10 on RTA is suddenly lost, the routing entry in RTA will become invalid. RTC, however, contains a route in its routing table to network 10 that is learned from RTA, and may proceed to advertise this as the best route for network 10 to RTA. Upon receiving this, RTA is able to update its routing entry to network 10 with the new learned route containing a hop metric of 2. Since RTC learned this route from RTA, when RTA proceeds to advertise this route to RTC, the route now contains a hop metric of 3, to which the cycle continues. Since RIP contains a limit on the hop count, when the metric reaches 16, the route will be deemed unreachable, and as such preventing counting to infinity. One of the problems with the counting to infinity process is that time is still required before the route can be deemed unusable, and so the network may not be stable for a period of time until such a hop count of 16 is reached. It is important for this convergence time, therefore, to be improved, and so another process to handle this is required. Split horizon is the means by which this is alleviated. Split horizon works by stating that a route that is learned via an interface cannot be re-advertised back over that same interface, such as where a route received from RTA by RTC on network segment 192.168.1.0 will not again be advertised back to RTA over the same link. If we return back to the example given, we can see in the case of the three routers the route advertisements that are typically generated, along with the metrics in each case. We can then consider a situation in which network 10.0.0.0 that is connected to RTA is lost. The loss of this route will in fact start another process in which the route is marked by RTA for deletion. This involves RTA proceeding to advertise network 10.0.0.0 to neighboring routers with a metric of 16 to effectively flush the route, and therefore the route will not be immediately removed from the routing table. If, however, during this period another advertisement is received by RTA for the route, such as in the case of the advertisement sent via RTC to RTB, RTA will again assume a valid route is present to network 10 via RTB, leaving the potential for an alternative counting to infinity loop to occur. In respect to the matter of convergence times that are affected by the count to infinity process in RIP, another mechanism was introduced that looked at improving the time in which RIP routes would converge. The poison reverse mechanism is considered an improvement on the split horizon mechanism, and works by ignoring the split horizon rule that RIP routes received on an interface cannot be advertised back over that same interface, and instead proceeds to advertise the route back, but this time with a metric of 16. This is done to effectively ensure that should a route be lost, it will not be inadvertently learned falsely via other means. We can again consider from the perspective of RTA, advertisements of network 10.0.0.0 to peering routers being met with a response that involves the same route with a metric of 16 being received by RTA. This effectively tells RTA that there is no other route via which network 10 can be discovered. If network 10 that is connected to RTA suddenly failed, the route would be immediately considered unreachable to RTA, with no chance for it to be learned via another route. This effectively speeds up route convergence by ensuring inaccurate routes are not learned and the count to infinity process does not once again occur. The update of the current status of routes is subjected to the 30-second periodic timer by which all updates are controlled. If a failure in the network occurs, however, having to wait a period of up to 30 seconds before sending notification of the change will often delay convergence. As a solution to this, triggered updates can be used, which pretty much ignores the periodic update rule and allows for notification of the change to be advertised almost immediately after the change occurs, and greatly reduces the RIP convergence period. The communication of RIP messages as introduced occurs periodically, with a default period set at around 30 seconds. However, it is important to understand exactly what information is carried to understand the way in which RIP operates. Messages for RIP are carried to UDP port 520 and are transmitted as broadcasts to each of the neighboring RIP routers. The fields represent the contents of a RIP header, which includes the command field that defines the message type being used. Periodic messages used to update neighbors are considered response messages. However, request messages are also supported. The version field defines the version of RIP being used. The current message shown relates to the original version of RIP, and therefore the version field is set to 1. The address family identifier refers to IP, and for which the IP address field carries the IP network address being advertised, along with the metric in the last field. This metric may be any value between 1 and 16. However, 16 denotes an infinite route that is unreachable. With the advent of newer and more capable protocols, the existence of RIP was unable to be maintained for commercial use in its current format. RIP, however, being a protocol with very little in the way of overhead, continues to be ideal for smaller networks, and as such a number of improvements were made to the RIP protocol. The extensions can be considered to have breathed new life into the protocol and allowed it to continue to function in the face of continually evolving networks. This resulted in RIP version 2 being formed, which in itself is not entirely a new protocol, but an improvement on the existing RIP protocol. One of the major factors was the need to resolve the issue of RIP operation as a classful protocol. We see, however, that following the extension of the message field, RIP now supports a field used to carry subnet mask information, enabling classless behavior to be supported. The version field distinguishes the extended version from the original by setting the version number as version 2. Other factors include the addition of authentication that is supported through the identification in the address family identifier field. We now also find that the advertisement of RIP messages are addressed using a multicast address of 224.0.0.9 to enable the messages to be handled only by those routers that are interested in receiving RIP messages. During the initial development of RIP, security was not a factor for consideration. However, as IP networks have grown, the importance of security in routing has increased dramatically. This has resulted in changes made to RIP that includes authentication, which allows messages to be accepted only when the peering router is able to be authenticated. This is important to prevent rogue routing devices from being added to the network that can effectively redirect traffic to other routes and compromise the network. Through authentication, unauthorized routers cannot participate as part of the RIP network. Coming to the message header, we see here that the address family identifier field is referenced as a string of F values, where the message is one of authentication, along with a field in the message to define the authentication type and a 32-bit authentication field, which represents the authentication password. We find here that RTB is sending the RIP authentication message containing the password of Huawei. It is expected that the password match the password set on RTA. If the passwords match, RTA will accept RIP messages from RTB. More recently, stronger methods of authentication have been incorporated into RIP to ensure the integrity of the security, as threats of compromise to existing authentication methods become more likely. These newer authentication methods within RIP support encryption, which effectively hides the true password to prevent it from being applied to other non-authorized devices. Increases in network traffic mean that a greater number of routes may exist between destinations, and often at times represent routes with an equal cost. Where such routes are equal, RIP version 2 is able to support load balancing of traffic. We can see here how network 10.0.0.0 on RTA may be advertised to RTD via two equal cost paths, for which both can be utilized to better manage traffic load destined for network 10.0.0.0 via RTD. The configuration of RIP requires only a few simple commands in order to allow for convergence between routers to occur. We can see that RTA wishes to advertise network 10.0.0.0 to the neighboring routers to allow them to be aware of the network and have a valid path back to network 10 for any packets destined for hosts within its network. Firstly, the router must enable the RIP protocol and process. The process represents an instance of RIP and is generally recommended that this process be the same for all routers. If a process number is not specified, process number 1 will be used by default. We can see this here in the parenthesis following the RIP command, in which the RIP protocol view for process 1 is entered. Under this view, we specify the use of RIP version 2 and the network that is to be advertised. The resulting process will see RIP version 2 messages containing network 10.0.0.0 being advertised to the neighboring routers. We can further manage the communication of RIP messages through a number of different commands. The first of such commands is the RIP metric in command that is used to manipulate the metric of messages being received by a RIP router. In this example, we can see this command applied under the Gigabit Ethernet 0/0/0 interface, for which it is stated that any routes received should have their metric increased by a value of 2. The message transmitted from RTA is associated with a metric of 1 upon transmission, which when received will be incremented by a value of 2 and added to the IP routing table of RTC with a metric of 3. As an alternative, it is also possible for the metric to be manipulated based on the outbound interface of the message. In this instance, we can see that at the point of transmission of the message via the Gigabit Ethernet 0/0/0 interface on RTA, the message is incremented based on the value specified in the metric out command, which in this case is 2. One point to be clear on is that the metric is incremented at the point of transmission, and so in this case, the metric specified in the metric out command represents the incremented metric value. This means that once the metric is received on the Gigabit Ethernet 0/0/0 interface of RTC, the metric will already carry a value of 2. In order to prevent loops from occurring, it is necessary to ensure that either split horizon or poison reverse is active on the interfaces participating in the RIP routing process. We will typically find that by default, split horizon is enabled. Where both split horizon and poison reverse are configured in VRP, however, only one can take effect. The example shows the commands used to enable both split horizon and poison reverse. However, in such a case, the poison reverse command would take precedence and the split horizon rule would be made inactive. Following configuration of the RIP protocol and parameters, we were able to use the display command shown here to verify the results of the RIP protocol configuration on a per interface basis. As we can see for RTC, this involves the configuration of the metric in command with a value of 2, as well as setting of the split horizon and poison reverse commands, which both show as enabled. However, as mentioned, only the poison reverse command would take effect. When the RIP protocol is enabled on a router, RIP will by default forward messages to the peering neighbors. There may be instances in which this behavior is not desired, however, such as where the peering network is not part of the immediate enterprise domain, and these routes are expected to be kept internal and secure. In using the undo RIP output command, RIP advertisements will be restricted. The internal network, however, is still able to maintain a connection to such networks through static routes that will not provide advertisements relating to the internal network. Another command is that of the RIP input that is used to manage how RIP routing information is handled by the receiving interface. The shown configuration involves the use of the undo RIP input command on the Gigabit Ethernet 0/0/1 interface of RTD. Through this command, all received RIP messages via this interface will be ignored and discarded. This prevents the interface from taking part in the RIP process and may even be used to restrict an entire router from participating in RIP. The same display command can also be applied to RTD to view the RIP status of each interface. In this case, we take a look at interface Gigabit Ethernet 0/0/1, on which we should recall that the command undo RIP input was configured. The resulting command output thereby shows the inbound RIP messages are discarded as a result of the disabled state of the input field. A similar command to that of the RIP input is the silent interface command. While the interface will not participate in RIP, it will continue to receive messages and update the routing table with the messages received. If the RIP input or RIP output commands are configured on the interface at the same time as the silent interface command, it is the silent interface command that will take precedence. For those interfaces that have been configured as silent interfaces, we're able to verify the configuration has taken effect using the display RIP command. The entry within the command will list those interfaces that are currently operating as silent, as we can see highlighted here. This then brings us to the summary for this section on RIP, in which we ask a couple of questions here. The first of those is, at which point is the metric incremented for advertised routes? Well, if we recall, the metric of advertised routes are always incremented at the point of transmission from the outbound interface. Secondly then, what configuration is required in order to advertise RIP routes? Well, we are required to configure the network command followed by the network to be advertised. If there are multiple networks, each will require an individual network command to be configured for each network.